Hello everybody, this video is going to be about types of IMFs. We've already learned about how some molecules are polar and some are nonpolar, and how that results in intermolecular forces when two molecules are interacting with each other. And so now we're going to learn about the types of intermolecular forces. So remember that the intermolecular forces are what's happening between neighboring molecules. We're going to be able to rank them from the weakest to the strongest, and then we'll start learning about each of the types. So the weakest IMF that we're going to learn about is something called London dispersion forces. We often just abbreviate that LDF. The next is what we call dipole-dipole. That sounds a little silly to say it twice, but when we have a polar molecule, it has a dipole, meaning it has an uneven distribution of charges. And so this is describing how we have two of those things interacting with each other. So that's why we say it twice, dipole-dipole. The strongest type that we're going to learn about is called hydrogen bonding. And actually, hydrogen bonding is a terrible name because bond implies that it's an intramolecular force between atoms inside a molecule, and that's not what's happening. It would have been a lot better if we had named it a hydrogen force, because that would imply that it's one of these weaker intermolecular forces. But unfortunately, the name hydrogen bond kind of stuck. So as long as you understand that it's not a normal bond, it's not strong enough, that when we say it's the strongest IMF, it's still very, very weak. It's still a weak force. Then that's great, as long as you understand it's not a real bond. Sometimes you may see the term van der Waals forces. Van der Waals forces is what it's called when we just combine all of these IMFs together, because it can be pretty tough to measure them individually, and so sometimes people just lump them all together and measure them as a big category called van der Waals forces. We won't use that term very much in this class, but if you may stumble across that on the internet or in textbooks. So let's look at London dispersion forces. So a London dispersion force is very, very weak and very, very temporary. Everything has London forces. A London force is going to result when we have anything with electrons interacting with something else that has electrons. What ends up happening is normally your electrons are spread out. You can see here we tried to spread these little electrons across the surface, and they're moving around randomly. Remember, the electrons buzz around inside their orbitals all over the place. Well, at any moment in time, just by sheer statistical probability, you might end up with the electrons on one side of the molecule more than the other. And when that happens for a very brief moment in time, you get a little bit of a negative side and a little bit of a positive side. So when that happens, you get that tiny little electrostatic attraction happening, a little tiny attraction. The big deal though is that it's temporary. This happens, in an instant, and then the next moment comes and the electrons have moved somewhere else. So that dipole is not going to stay permanent. So we call this an instantaneous dipole. It is very, very weak and very, very temporary. This is the type of interaction that nonpolar molecules might have that allows them to stay close enough together to still become a liquid, even though they're nonpolar and there's not a lot of interaction happening. So one single London force is pretty weak, but you could, in theory, get more and more and more London forces adding up, and if you have enough London forces, it could have a decent cumulative effect and end up decently strong, but each London force is very weak. Okay. Next, just want to make sure we really understand that everything has London dispersion forces because everything has electrons. Everything has a chance for, in a brief moment in time, for the electrons to be unequally distributed because they're buzzing around randomly. So just sheer chance they may end up unequal. One thing that's important to know is that the bigger your molecules, the more London forces you're going to have, because you're going to have more places to get that temporary unequal distribution. So for example, C8H18 will have more London forces than C3H8 because it's bigger. Now, in real life, this is pretty tricky to measure because you have to take into account the surface area of the molecule as well as what we call the polarizability, which is how easily can the electrons be moved around. Now, that's not something that we can easily predict at our level of chemistry. We're not going to be using molecular modeling software to measure the surface area and the polarizability of these molecules. But there is kind of a quick and dirty way we can figure this out, a little quick trick that will work most of the time, and at our level of chemistry, it's the best we can do. So the trick is that if you count how many electrons it has, the more electrons will be the one with more London forces. It's not perfect. It doesn't work always that way in real life. It is more complicated, but for what we can do, that's how we're going to do it. You count the electrons. So if you have to rank two things that are nonpolar with their London forces, more electrons, more London force. All right, let's move on to dipole-dipole. Dipole-dipole only occurs in polar molecules because the big deal here is that we have a partial negative attracted to a partial positive, but it's permanent. Because these molecules are polar, they will always have one side that's a little bit plus and one side that's a little bit minus, always. And so because of that, this electrostatic attraction won't disappear like a London force does. This will always exist. And so a dipole-dipole is much stronger than the London force because it's a bigger difference in charges and because it's permanent. And so a dipole-dipole force is a little bit stronger than a London force. The last one I think is tricky to explain. It sounds more complicated than it is. Once we start doing some examples, this one becomes pretty easy because there are not a lot of examples that will have this. So we'll go over this hydrogen bonding, get it down in your notes, but then don't stress too much about it. Just pay attention and make sure on your practice problems you're making note of the hydrogen bonds, because when you see more and more examples, it'll become more and more obvious what it is. So the funny thing about hydrogen bonding is that it's just a type of dipole-dipole. It's like a subcategory. It's a more specific dipole-dipole. It is a really, really extra strong dipole-dipole because you're going to have a really big difference in your charges, in your electronegativities. So you're going to have a really, really partial positive side and a really, really partial negative side. And because it's such a big difference, even though it's just a dipole-dipole, that extra strength means it's extra important because it impacts a lot of the properties more than expected. Very, very important in biology. We'll go over a couple of those examples in our next lesson. So you have to have what we call H-NOF lone pair. It's a silly little way of remembering this. So what you have to have is you have to have a hydrogen atom that is directly bonded to one of these three atoms. Any of these three work. It can be a nitrogen, it can be an oxygen, or it can be a fluorine. It doesn't have to be all of them. One of these is fine. Whichever of these atoms, whichever of these NOFs that you have, it also has to have a lone pair. If the nitrogen, oxygen, or fluorine does not have a lone pair directly on it, you won't have enough negative side, so it won't count. So you have to have H-NOF lone pair. So let's look at an example of water, the most classic example of hydrogen bonding. We have a hydrogen. It is directly attached to one of our NOF atoms. This time it's an oxygen. And the oxygen has one or more lone pairs on it. That makes a really, really plus side and a really, really minus side. This end is really pulling the electrons towards it. That's going to allow this electrostatic attraction between the molecules, the IMF, the intermolecular force. This is just a dipole-dipole, positive and negative being attracted, right, like here, but the extra strength makes it the hydrogen bond. So to kind of summarize that, you're going to have an attraction between your partial negative on the lone pair on one of these atoms, and it's attracted to the hydrogen end, because that's the positive side, of one of these combos. And once again, that electrostatic attraction is what draws those molecules towards each other. So you should have a little flow chart in your notes. Some people find the little flow chart helpful. It forces you to take it one step at a time and think about the molecules and walk yourself through the decision-making process when you're trying to identify what type of IMF you have. So the first question you should always ask yourself is the molecule polar? If it's not polar, your only choice is London dispersion forces. If it is polar, you have to ask yourself, does the molecule have any of the following bonds? HN, HO, or HF? And now I'd like you to add this to your flowchart in some kind of a bright color, big, bold, obvious, yellow highlighter, red pen, exclamation points. Remember, it has to have that lone pair on it. So it's not printed on your flowchart because I want it more obvious, since I can only print in black and white for you. I want you to add this in a bright, obvious color. If you don't meet these special criteria, then it's just a normal dipole-dipole. You also have London forces present because everything has London force, remember? So if we ask you to list all the forces that are present, you would say dipole-dipole and London. 90% of the time, we only care about the strongest force, right? The London forces is not going to contribute much when you have a dipole-dipole. The dipole-dipole is the main contributing force. So if we ask for the dominant force, or we just ask for what the force is, you can just list the strongest part. If you do have these special criteria, then it's specially called a hydrogen bond, which is just a fancy dipole-dipole type, a subcategory. And you also have London force, right? Because everything has London forces. But the dominant force would be that hydrogen bond. Okay. The rest of the notes are going to be going through some practice problems. So while we go through these, I'd like you to pause it when asked, actually give it a try. That's going to be part of your learning process. Okay? You should have already copied this down in your notebook. You should have this chart. In order to do this, you'll have to know what the Lewis structure is. So in the box where it says molecule, you could draw your Lewis structure. If you don't have quite enough space there, you could add it to your justification box or make a little flippy, it doesn't matter. So let's start with the first one, C2H6. I'd like you to pause the video and try to draw the Lewis structure and try to decide if it's polar or nonpolar. All right, so your carbons should be attached to each other because the hydrogens have to go on the outside. So your structure should look like that. If you use dots for your bonds instead of lines, that's totally fine, not a big deal. Now when you look at this structure, the left is the same as the right, the top is the same as the bottom. So everywhere on this molecule, if you were to look at it from the outside, there would be no unequal distribution of electrons. Everything would be spread out nice and evenly. That makes it nonpolar. If you look at your little flow chart, if the molecule is nonpolar, the only option for IMF would be London dispersion forces. So the dominant IMF here would be London dispersion, and your justification would be you explaining that this is a nonpolar molecule, and when you have a nonpolar molecule, your only option is London forces, because there's no permanent dipole. Everything's just temporary here. All right, next one, CH3OH. If you notice, they chunked the formula, right? They tried to give you a hint. You're going to have 3 hydrogens attached to the carbon, and then you're going to stick on that oxygen, and then put the last hydrogen onto the oxygen. Pause the video, try to draw your Lewis structure, and decide if it's polar or nonpolar. All right, this is what our Lewis structure looks like. If we look at this molecule, we can see that the top looks the same as the bottom, but the left does not look like the right. It is unsymmetrical. This oxygen is more electronegative, so it's going to be pulling some of those electrons towards it. And so we end up with one side that has a dipole, or we end up with a dipole, one side negative, one side more positive. So it's polar. Next, we have to ask ourselves, okay, if it's polar, we know it's dipole-dipole, but does it meet the fancy criteria to be a hydrogen bond? Does it have a hydrogen directly attached to a nitrogen, oxygen, or fluorine? And does it have a lone pair on it? And it does. If you look right here, hydrogen directly attached to oxygen, the oxygen has 1 or more lone pairs on it. So this is a hydrogen bond. So you can put that the dominant force is a hydrogen bond, and your justification is explaining that it's polar, so it has a dipole-dipole, but that it also meets the fancy criteria for a hydrogen bond. It does have that H-NOF lone pair. All right, let's try the next one. Now, one of the things I want to show you on this one, we're just jumping straight towards my picture, is that you need to remember that the lone pair on a center atom bends the molecule down. Do you see how those fluorines are pushed down out of the way, kind of like on a water molecule, it ends up bent? That's going to mean that while the left and right are the same, now the top and the bottom are different. So since it's been a while since we drew Lewis structures, I don't know if you remember that this lone pair can bend things, and that changes the shape. Now we can see that this is a polar molecule. So if it's polar, we know that it's dipole-dipole, but we have to check to see if it meets the fancy criteria to be an extra strong dipole-dipole. Does it have the criteria to be a hydrogen bond? And it does not. We don't have hydrogens. They're not connected to those fluorines, right? So there's no hydrogen bond. It's just a regular, simple dipole-dipole. Okay. Let's try the next one. This time, pause the video and you try to draw your Lewis structure for NH3. All right, this should be very similar to the last one. We have a lone pair bending it down. I don't know if you remember this or not, but sometimes people like to use these little triangles to try to make it look more three-dimensional. The regular bond is just lying flat on your paper. The solid triangle is trying to pop straight out at you, kind of like a 3D movie. And then the dashed line is trying to be going into the paper away from you. So they're just trying to show you that 3D shape. You don't have to do that on your paper, but I want you to just be comfortable if you see it. So now we can see the left and the right are the same, but the top and the bottom are different. The electron density is going to be higher up here at the negative end of this molecule. Right? Remember that it bends those hydrogens down, having that lone pair. It's polar. So we know it's at least a dipole-dipole. Now we have to see if it meets the fancy criteria to be a hydrogen bond. Is it strong enough to be not just a normal dipole? So does it have hydrogen? Yes. Is it attached to one of the NOF atoms? Yes, this time it's nitrogen. Does that nitrogen have a lone pair on it? Yes, it does. So we can see here, we also have one here and one here, right? I just highlighted one as an example. So this will be hydrogen bonding. All right, two more. This one, if you remember from when we learned Lewis structures with the chunking of the formulas, this was one that people got wrong a lot. This is a good one to practice. Make sure that you really, really remember what this structure looks like, where you have the hydrogens attached to the carbon, and then the oxygen is attached onto that carbon as well. And the only way to make the numbers work is to make that a double bond. So now we have to look at this and say, okay, is it polar or non-polar? Well, the left is the same as the right, but the top and bottom are different. Way more electron density up here, so this is polar. Does this meet the criteria to be a fancy dipole-dipole? Is this going to be a hydrogen bond? People make the mistake of saying, yes, there's hydrogen and there's oxygen, it's a hydrogen bond, and they don't look to see how things are attached. Remember, in order to count as a hydrogen bond, the hydrogen has to be attached to nitrogen, oxygen, or fluorine. They can't just be somewhere else in the molecule. They have to be attached. So if you look here, we have hydrogen, but it's not attached to the oxygen. So we do not meet the criteria. That hydrogen is not connected to the oxygen. So this is not hydrogen bonding. This is just a simple dipole-dipole. And I'll tell you right now, every time we put this on a quiz, there's bound to be people who miss it. And it's because they won't take the time to draw their Lewis structure, or they don't draw a correct Lewis structure. So it's important that you don't forget that previous chapter. All right, the last one. The top is the same as the bottom, but the left is different than the right. That makes this polar. Yes, we have hydrogen. Yes, we have fluorine. Yes, the fluorine has a lone pair, but the hydrogen is not attached to the fluorine directly. Yes, this has a dipole, but it's not a strong enough difference to be a hydrogen bond. So it does not meet that special criteria. So this is just a dipole-dipole. Okay. In our next lesson, we'll learn how to kind of rank things based on their IMFs. For now, we're just trying to make sure we understand the general idea of how we determine which IMF is present, and then that you know London is weakest, then dipole-dipole, and hydrogen bond is a extra strong type of dipole. If you would like on your own, you can watch a crash course video on liquids. The link is in the PowerPoint, or you can just go to YouTube and search for crash course liquids. Even though it's titled liquids, this is actually about IMFs, because the IMFs are what hold molecules close enough to become a liquid. That's why he called the video liquids. But it's a great recap and summary, and goes over all the IMF stuff that you've learned so far. So that'd be a great one to watch just as a little refresher for you. All right, everybody, that's it for this video. I hope this was helpful. Bye.